Now that we've had some practice with some basic probability and our probability rules, the addition rule and the multiplication rule, and also with conditional probability, let's now take a look at some more complicated probability experiments with some larger sample spaces. So we need to know how to count the number of ways an event can happen. And we need to know how many total possible outcomes there are. That's how we calculate the theoretical probability of an event happening. How many ways can the event happen divided by how many total possible outcomes. And for right now, we've been doing that, but our events have been pretty simple. Now let's get a little more complex and talk about counting. Let's try this example, and I want you to guess the number of total possible outcomes first. Don't try to reason it out, ballpark it. Write down a number, write down a guess. And then draw a tree diagram, and we'll use the tree diagram to come up with our total possible outcomes, and then talk about how to count, but without drawing that tree diagram. So the example, you buy a lunch special that gives you a choice, one each of 3 sandwiches, turkey, ham, or veggie, 2 types of chips, plain or barbecue, and 3 drinks, water, iced tea, and lemonade. So make a guess. Take a moment, guess. How many different possible outcomes can you have? Write a number down. Okay, now let's draw a tree diagram. So for my tree diagram, I'll have a start. We always have a start node. And I first have one each of 3 sandwiches. So I'm going to have a branch for my turkey sandwich, a branch for my ham sandwich, and a branch for my veggie sandwich. And then I have 2 types of chips. So I have plain or barbecue, and I'm just going to use B for barbecue. And then 3 different drinks. So we have water, tea, lemonade. There's a lot going on here. So how do we figure out what are my outcomes for this probability experiment? I follow the branches of the tree. So at the start, turkey, plain, water, turkey, plain, tea, turkey, plain, lemonade, and I finished my first grouping with the turkey and the plain chips and all the drinks. So then I can go to the next one. Turkey, barbecue, water, turkey, barbecue, tea, turkey, barbecue, lemonade. And so I have 6 different meals that contain a turkey sandwich. And I can repeat this for ham, and I can repeat this for veggie. So let's go through that pretty quickly. And I can follow all of these branches and write out all of my different possible meals that I can have with these different lunch choices. Now, how many do I have here? Count them up. We have 18 total outcomes. Okay. Well, if you guessed that, great. How did you guess that? Why did you guess that? If you guessed something differently, why is it different? Think about it. Remember, it's okay to be wrong. We make mistakes all the time. The important thing is learning from them. And it was a guess. I'm not expecting you to guess and get it right every time. So with this number 18, take a look at the original question with the choices. We had 3 sandwiches, 2 kinds of chips, and 3 drinks. Is there a way to take these 3 numbers, 3, 2, and 3, and do some operations on them and end up with 18? Yeah, there is. If you don't see it right away, remember, it's okay. Notice for each sandwich, I get 2 branches for the chips. For each chip, I get 3 branches for the drinks. If I multiply these numbers together, 3 times 2 is 6. 6 times 3 is 18. This example illustrates what we call the multiplication rule for counting, also known as the fundamental counting principle. Anytime you have the word fundamental in a math lesson, it's a pretty big deal. 2 more things to think about before we get started. When you are dealt several cards in a game, like poker, does it matter in what order you receive the cards when you are dealt them? Do you have a different hand if you have a king, a queen, and an 8 of hearts versus an 8, a king, or a queen of hearts? Is your hand the same? Or does the order that you receive the cards matter? Is it important to the game? For some games, it is important. But for many games, particularly poker and card games, it's not. Think of Old Maid or Go Fish. These types of games, the order in which you are given the cards does not matter because you can rearrange them in your hand. What about when you run a race? Does it matter if you come in first, second, or third? Does coming in first mean something different than coming in third, or sixth, or last? What do you think? Is coming in first different from coming in third? Yes, it's very different. We think about the Olympics. Winning gold is very different from winning the bronze or placing fourth. The order does matter in running a race where the places are important. We are going to expand on this, talk about it some more. Both of these concepts, they have very special ways of counting related to that fundamental counting principle. So we'll see these types of problems coming up. Take a moment. If you can, pull up your textbook. See if you can find definitions for these words. Write them down. The fundamental counting principle has several different names. You saw that I called it the multiplication rule for counting. In our textbook, it also calls it the multiplication axiom. Axiom is just another fancy word for an important statement. So you have a definition in your textbook, and I know I told you to go to your textbook and write it down, but I want to make sure that when you have these definitions, that you have multiple ways to connect to them. Definitions aren't intended for you to memorize word for word, but for you to get a deeper understanding. So sometimes I might write the same definition that's in the book, and sometimes I might write slightly different wording. Use what makes the most sense to you. Use the definition that is easiest for you to remember, that's easiest for you to connect to and understand. That's the important part with these definitions. Remember that you just need to apply them to the situations at hand. I'm not going to ask you to write out the definitions. So similar to what's in your textbook for the multiplication axiom, I'm going to write down a slightly different version, again, just to give you different wording, hopefully that one of these 2 definitions you can connect to and understand better. So the fundamental counting principle, also known as the multiplication axiom or the multiplication rule for counting, if there are m ways, and m is a number, of doing something, and n ways of doing another thing, then there are m times n ways of doing both. We saw this with the roll of the die and the flip of the coin. We see this with the sandwich and the chips and the drink. So the counting principle is not limited to only 2 tasks. We can have multiple tasks, 5 tasks that we're doing together. And if we have different numbers of ways of doing these 5 tasks, we would multiply those numbers together and figure out the total number of ways of doing all 5 of those tasks together. Factorial is a mathematical operation. Just like multiplication, division, addition, subtraction, exponents, roots, factorial is another operation that we use in mathematics, a shorthand, if you will. The symbol for factorial is an exclamation point. So I'm going to use the letter N. So N factorial means that I start at N and I multiply all the numbers n and below until I get to 1. And when I get to 1, I can stop. So I'm going to write it down as formal notation, and we're going to do some examples. Okay? So n times n minus 1, n minus 2, n minus 3, all the way down to 3 times 2 times 1. An example. 4 factorial would be 4 times 3 times 2 times 1. And we would just multiply those four numbers together. 4 times 3 is 12. 12 times 2 is 24. 24 times 1 is 24. So 4 factorial is 24. There is one special little note in here. N factorial works for all positive integers, 1, 2, 3, 4, 5, 6, etc. But there is one number that it also works for. It works for 0. 0 factorial is 1. You're probably thinking, why? Because it's a little weird. But I will tell you that the 0 factorial is sort of related to this idea that any number to the 0 power is 1. So let's explore this for a moment. We get hung up on factorial because of this very statement right here, the 0 factorial equals 1. So I'm going to slide over to the side here, and we're going to take a moment, recall that any number to the 0 power is 1, and here's why. Let's take a simple number, like 2. 2 to the first power is 2. 2 squared. Remember that exponents we multiply that many times together. 2 to the third would be 2 times 2 times 2, which would be 8. And hopefully you can see the pattern. If I just increase my exponent by 1, I just need to take the previous number and multiply by 2. But what happens if we start at the bottom and we try to work our way backwards? So starting at 32, 32 to 16, how would I get there? Divide by 2. 16 to 8, divide by 2. 8 to 4, divide by 2. 4 to 2, divide by 2. Mathematics is all about patterns. And so we see this pattern of dividing by 2 each time. So what should be the case for 2 to the 0 power? Well, 2 divided by 2 will give us 1. And it continues. 2 to the negative 1, we can talk about negative exponents. 2 to the negative 1 power, we would just keep going. Divide by 2. We get 1/2, etc. We can keep going. Okay, now how in the world is this related to 0 factorial equaling 1? So let's start out with 1. 1 factorial. 2 factorial is 2 times 1, which is 2. 3 factorial. Yeah, 6. 4 factorial, we just did that one. 4 times 3 times 2 times 1. 5 factorial. It's a little bit bigger. Factorials grow really fast. And it keeps going. But let's do the same thing for the factorials that we did for the exponents. Start with the 5 factorial. How do I go from the 5 factorial number to the 4 factorial number? I divide by 5. How about from 4 factorial to 3 factorial? 24 to 6, I divide by 4. 6 to 2, divide by 3. 2 to 1, divide by 2. Notice the pattern. 5, 4, 3, 2. What's the next one? For our 0 factorial. Right. Divide by 1. 1 divided by 1 gives us 1. There's another physical reason why 0 factorial equals 1, and we'll talk about that when we get into permutations. So some more definitions. We have a permutation rule. We actually have 2 permutation rules and what's called a combination. And these 3 rules are all based off of the factorial operation, which is why we have to talk about it. So for permutation rule, where all objects are different, we can also say repetitions are not allowed. We cannot repeat something. We have some notation, and I'm going to write all of it down that I can think of, just so that we have that information there. One notation is NPR, where the N and the R are small subscripts. We also have the notation P parentheses N comma R. Sometimes you'll see that on a calculator. Both of these mean permutation. And the formula n factorial over n minus r factorial is how we would count the way of ordering things if everything is different. How many ways to order r objects from a set of n different objects? So we may not take all of them if r is smaller than n. We don't have to take all of them. Let's say we have the numbers 1 through 9, and I'm going to put all those numbers in a hat and draw 3 of them out and arrange them in an order. So the first one pulls out, the second one comes out, the third one comes out, and I set them down. This formula will count how many different arrangements I can create in that situation. This second permutation rule is all about objects that are same. So I'm going to write up here, we're going to talk about this in a little more detail in example 3 with the word probability. And I know that this comes up in your lab assignment in part 3. So this formula is a little important for us in a couple of different ways to help us count how many heads and how many tails when we flip a coin. So permutation rule, and I should make a note, permutation is another word for an ordering. We're ordering objects or arranging them, order or arrangement. Permutation rule for objects that are the same, number of permutations of n objects, and we're going to arrange all n of them. If we don't arrange all n of them, it becomes a way more complicated formula, and that's too deep for us to go right now. Permutation of n objects with R1 objects of one kind, R2 objects of another, and so on, is given by the formula n factorial divided by R1 factorial, R2 factorial, all the way to RK factorial. The problem in the lab, I did the problem 5 heads and 5 tails, and I wanted to know how many different arrangements there were. I have 10 total, 5 heads and 5 tails. And so I would calculate 10 factorial divided by 5 factorial. And that would give me my number for how many arrangements of 5 heads and 5 tails I could get when I flip a coin 10 times. But we'll see this one again one more time in example 3. For a combination is not an ordering, it's just a grouping. A combination is a set of R elements taken from n distinct elements in which order or arrangement does not matter. So up here with the permutation rule, an example is running a race, getting gold, silver, bronze, 4th place, 5th place, etc. That order matters. A gold is very different from a silver, is very different from 4th place. So for a race, when you're running a race, the permutation, the order is important. So we would calculate the number of ways we could have runners finish a race by using the permutation rule. For a combination, we can consider a combination as like the cards being dealt in a game of poker. Instead of racing for a medal or for a placement, if we were racing to qualify for the next round. A qualifying race takes the top so many. Let's say a qualifying race takes the top 5. Then it doesn't matter if you come in 1st or 5th. You qualified for the next race. So you have to run in the medal round. So there is this difference just within racing, whether you're qualifying for the next race or you're racing for placement. When you're qualifying, that's an example of a combination. The order, the arrangement does not matter. And you'll see the formula for combinations. It looks similar to permutations, but it's got an extra divisor in it. We're dividing out the arrangements of the same elements. So cards in a card game, for example, when you're being dealt cards or when you're qualifying for a race. So for a combination, A, B, C, and C, A, B are the same because they're the same letters, just in a different rearrangement. So the formula, we have NCR, just like our permutation NCR. We can also write this as CN, R, just like our permutations. Just know that it's combinations instead. And we'll have n factorial divided by n minus r factorial. There's the permutation formula. And then we tack on this extra r factorial on the end to divide out the same objects with different arrangements. Okay, that concludes all our definitions. And I know, especially for these formulas, you might be a little shaky. That's okay. In the next examples, we're going to apply them, work through talking about why we would use one versus another, and hopefully start clearing up some of the muddiness that might be occurring just with those definitions.